Hi, and welcome to part 2. In part 2, we will build a neuron that will be able to classify the images based on the imports here. So the objective of this section, or the objectives, is to write a sigmoid function and to write a function to initialize the logistic regression parameters, W and B. We're going to write a function that implements forward propagation, backward propagation, and the learning rate, and then we're going to merge all of the above in a single function and call it model. We're going to adjust the learning rates so you can see what different learning rates do to the accuracy. We're going to visualize our learning rates, so we're going to plot a graph with different learning rates and then show you how to add your own image that is not included in the train set or the test set, but to import it directly into the model you've created. So let's do a quick recap of the logistic regression. For example, xi, so I is the number of the training example, being it 1, 2, 3, 4, or 5. The values is the column vector that you've created here from the train set x or the test set x. We're going to pass it into here as an x. W and B will be initialized as 0. In the future, we're going to see neural networks WT should be initialized with a random number rather than 0. But for this example, we will just initialize it by 0. The output would be z. We're going to pass this z into a sigmoid function, which is going to round it up to either down to 0 or up to 1, which gives you the y hat, and then we will know how close it is to the actual value y. For this purpose, y hat will also be called a, which can also be referred to as the activation function in this case. Here you see the loss function for that single value. So I here donates the number of the training example being used, being it 1, 2, 3, or up to 458 training examples for our train set. And the cost basically will be calculated by dividing the average over the total sets. So let's start by defining our sigmoid function, which is right there. Simply call it sigmoid, taking a single value z, as you can see in that case. And the equation is 1 over 1 plus the exponential of minus z, and we use the numpy array. We use the numpy methods, and we simply return it. So that's our sigmoid function. Next, let's initialize W and B with the zeros. So we need a dimension to ensure that we can work out with our matrices, since different dimensions won't work. It doesn't look right. Yeah. So just take in the dimension and make sure it's in the right shape, and b is a real number. Just return both of these. So now we've initialized a function to initialize our parameters of the logistic regression with 0. Now let's implement our propagation. So it will take in the W and B we created, and it will also take in our input x, which is the image, output y. We'll also get number of iterations. So how many times do you want it to do the forward and backward propagation? 5 times, 10 times, 20 times. Of course, the higher you do it, the more likely you will get it accurate, the learning rate. So how fast or how slow do you want it to move in every iteration? So we'll just create a list with our costs here, and that is basically the cost function here. So what is it? So the only for loop that we really need is the number of iterations, whether it's 5 iterations, 10 iterations, 1,000 iterations. Everything else will be vectorized. So the first thing we need to get is the shape. So how many training examples do we have? And that is located at x.shape1. And then let's implement our for propagation. So here will be get number of examples. So we get our forward propagation, and that will be the sigmoid that we just created here. So sigmoid. Make sure the parameters. Oops. Okay. Let's make sure this is correct. Oh, that's where the parameter went weird. Well, yeah. Yeah. So basically here what we got is the sigmoid of the z, and the z is basically the linear function up here. So that's the forward propagation. The next step is to then just calculate the cost function. So of this neuron. So it's a single neuron. It takes in the x. It takes in the x as input. It calculates the a sigmoid, and basically you want to get the loss function, and that will be minus 1 over m. So basically what I'm doing is I'm converting this into code. With the sum. Okay, so this is our forward propagation. So now we've calculated our cost function. Now we can do our backward propagation, and that's derived from our computation graphs. So in one of the lectures we have shown how do you derive this, and it's basically the dot of a, if you remember, it's a minus y. It's one of the lectures we explained this in details. Divided by the total number, and then dB. Yeah, these were the equations. Actually, since these, we don't really need this, since we just need to subtract. These are both values we have, so we can just do this directly. Yeah, you can just do this directly. And then we update our learning rate, or R values, with the new values and everything. Just copy it. Oops. I'll try to go get the equations now. So for those who don't remember or haven't watched those slides. So basically, if you remember this slide, with the gradient descent, the global minimum, and the partial derivative, the W and the B, which are the parameters of the logistic regression, was this equation here with the learning rate, and the derivative, the alpha here is the learning rate, and the dW and the dB are these values, and the backward propagation was calculated in this slide here, where we showed that going from here to here will give you the dW, and the other way will give, and continuing on will give you the dB. Sorry, the dB will be from here. So if you don't remember that, please go revise that lecture again. And I remember it was calculated down here. Okay, so now we have implemented the forward propagation, the backward propagation, and we try to calculate the new parameters. for W and B, and let's save them in dictionaries. So this is just for convenience, so we can just extract them later. So just go make sure this is right. Let's also save our new gradient descent values, which are the derivatives, which is the change in slope basically. Yep, let's take in our dB. The print cost is just like, instead of printing every single cost, if you have like 1,000 iteration, then you can say if print cost, which basically means if it's true and printed on the 100th value, just print the cost. Yep. So we can just print this if the iteration is in the ith 100. Yeah. Let me just make sure. Actually, this is still empty. Yeah. And also append the value every 100th. So if we are in the 100th iteration, which is basically for I in range of number iteration, then let's fix our indentation here. Okay. If we are in the 100th iteration, yeah, I can't mouse. Yeah, then costs not depend. Oh, let me fix the indentation. Okay, I just had these on Jupyter Notebook, which auto fixes the indentation. And now let's go a bit from the for loop and return the param, the gradient, and the costs. Okay, is something seriously wrong with the indentation here? This one. Okay, so there, I forgot this. Oops, I think we all the fixing has led to destruction. Now, these two things here should auto fix it usually. Okay. So now we've implemented a sigmoid function. We initialized with 0. We have also implemented the forward propagation, backward propagation, if I don't have typos there, iteration and the learning rates. And now we're going to implement the predict. So it will take in the two parameters really that you've just created with the logistic regression and the input value. And basically, by having these three values, you should be able now to go and predict from what you have versus what the actual value is. So again, which get the training example. So where are we again? So give me that, and I'll try to show you, try to remember in the model or when we input to make sure that you see that the number is there. It's the -1 transpose, if you remember. In the earlier part 1, we said -1 infers the size. Maybe we can scroll up and see. Yeah, so it's right here. So this is the RGB, the X value, and this is the number of examples. And you need that M for this part here. So that's M, really. Oh, it's also called M here. And why predict? That should also start with 0. So it's just an empty NumPy array. And it will have one M, so that will then look like the label where we printed it earlier. Okay, it's not here anymore. When we printed the labels, so maybe just grab this really quick. Oh yeah, because it's not the way we've done it. We've done it this way. Yeah, so it has to be in this form here. And if we click on the shape of this, there we see 1 by 458. So we're just trying to say 1 by whatever you pass it in, 458 in this case. And we also want to make sure W is also reshaped correctly. Also, we explained that in one of the lectures. So it should have One, of course, it's going to be for a single training example, and this here is going to take the 12,000 something something value we have, which corresponds to this here. So W1 and W2 should be the same as the amount of X that are being given in. And then now we can just pass it all to our sigmoid function, which we can just copy from here. Yeah, we can just here, so it's clear for you to see. And basically iterate over the shape of the activation and give me my y predict, or let's call it y prediction. Give me my y prediction and append it so I can see. And this is just a short fancy way to write an if statement, so just compact. So you want, if it's less than 0.5, just put it at 0. And if it's more than 0.5, put it as 1. And this is like in the sigmoid function, if it's 0.66, then round it up to 1, or round it down to 0. And please give me back my value. Okay. So now we got the predict, and now let's put all of them together in a single model. So we just call that model, and then the model calls all these functions. You can also create a class if you want, but perhaps this is easier for beginners. So take in the X train, take in the Y train, take in the X test, and take in the Y test. So the X train and its values, and the X test and its values. So that's your test. So Y is what the actual answer is, whether this is a bird or it's not a bird, or in our case bird or not bird, which is the number of classes we created. The user should be able to also pass the iterations, the learning rate, and if you want to print the cost or not. And this should be corresponding to this propagation, which we just created. Okay, so W and B should be initialized with zeros. Again, in the future you shouldn't be doing that in a full neural network, but this is just a simple example. So it's going to take the shape from X train. Then we will need all of these, which is the new parameters, the gradient, and the cost function. And again, that's simply a straight copy paste from here, so we don't have to. Sure, no mistakes. So call propagate, pass in the W and V from these initialized 0. Maybe, yeah, let's change this to take in the X train set and take in the Y train set. So that's okay. And the number of iterations is the same, the learning rate is the same, and the print cost is the same. And this function is gonna return this 3. So give me the W and the B. And these are going to be extracted from this dictionary here. So we'll just say do that and do that. And now you would want to give me what's the Y prediction on the train set. Since now you have the values of W and B, so you're going to tell it, okay, here is your W, here is your B, and here is your train set, and please tell me what is the value, and it's the same for the test set. So what is your value with these W and B that you have figured out, and yeah, the X test. Okay, so we're basically telling it, give us your values that you have predicted out of your cost function by passing it into the predict and making sure it's rounded down or up. Let's just print it really. So the training accuracy and the test accuracy, and I've just created these really here just to make it more accurate. So basically format it with the 100 and get the mean by subtracting the Y prediction train from the actual value of y train and the y prediction test from the actual value of y test, and this is just simply multiplying it by 100, so you actually get a percentage. Okay, let's just create a dictionary to output all of this. I've already written it. It will be in the notes, so you can just straight copy it. So there we go. So just a nice little dictionary here. Let's make sure it looks yeah. So I just clicked on here to clean it up a little bit. Yeah, so put the costs in the cost, and then you just have a dictionary of values. So what was the W, what was the B, what was your learning rate, at what iteration, and what were your costs in the Y prediction and the test. So we can see already here I did something incorrect. So there we go. And this looks much better. Give me back my D, please. Okay, so let's see what invalid syntax we have. Yeah, because we copy paste it. Now that looks so. Now let's just call our model. So if we scroll back to part 1, we have our train set X and test set X, and this can be simply passed to our model here as our X train and as our Y train. So train set X and our train set Y, which is the actual labels. Same tests set X and test set Y. This is completely up to you. I would say 1000 iteration. We'll set the learning rate into 0.001, but 0.001, sorry, but we'll adjust the learning rate so you see how different rates affect the value. And yeah, st underscore. Right, so let's see what we did wrong here. We got a capital letter. We got a naming error. Name Y is not defined. Which line is this? 12. From the propagate, let's see what we missed there. We used small letters. Let's try going again. Unsupported operand. Oh yeah, this looks super wrong. So let's just fix it. Then maybe will work. Y is not defined again. Wow, that was a lot. Oh yeah, the capital letter. Caps. Okay, let's take a look now. Ooh, there we got something. So you can see the cost function is going down and throws us another error. Ah yeah, that looks like a typo. In our predict, what did we do wrong? Zeros. Spelled it, so let's try now. Calculating the cost function again. Okay, there we are. So we see the cost function on every 100 iteration, because that's what we did. So we did 1000 iterations, so you have to have 10 here, and the train accuracy was 88% on your train set and 79% on your test set. So in the folder that we created the train set in, this model has successfully predicted 88% on it, and on this test set you predicted 79% on it, which is pretty good. Now in the next function, let's see what happens if we adjusted the learning rate. What are the values? So let's say our learning rates, let's put a smaller one, 0.0001. This is really small, or not that small, and then the one we just said we used, and one bigger. So we're passing these 3 parameters here now. And let's see how it looks. Let's make it more visual. Let's print it. So just gonna take it directly. Okay, so we just passed into our model here the values, the train set X, the train set Y, the test set X, test set Y, and we said give me 1500 iterations, so it's 1000 more, and the learning rate I is that one, and I'm not printing this time the cost function, and then this is just for the plot. So I just got that straight away. So when the learning rate is 0.001, what is our train set accuracy and our test set accuracy? So our train set accuracy is 83% and 75%. Yeah, I call it model, right? Right, so it's model. So what's this throwing? Oh yeah, models. Well, where is models when you already got a model? Let's try one more time. Okay, I'm doing something. Let me take a look. Well, I'm creating a new variable in this case. Yeah, well, yeah, I forgot to create a dictionary. Now it should work. So we got the learning rate is 0.001. So what is our train set and test set accuracy? So it's 83 and 75%. Now we should get the same value as this now, since it's the same training set. Oh, actually changed a bit. Oh yeah, because we increased the number of iterations. As I said, as you increase the number of iterations, you're more likely to get a higher accurate value. In this case, the training set went up by a little bit, but the test set has increased by more. And here we see when it's 0.01. Okay, so when we increase the learning rate to 0.01, our train accuracy went up to almost 100%. So we can start talking about overfitting here. But in future lectures, we will introduce optimizations and hyperparameters. So now we see a graph here. So with 0.01, you see it started to, the cost went down much more than the others. And this is the number of iterations. So at the 100th iteration, you see where it is at the 0 iteration, and then almost at the 1500 iteration, you see where it reached. Okay, so this is really almost that. You can get a random image online from the internet, or an image that you already have, and see how well your model performs. So I'm just going to go copy one that I already have. So this is just the path. Again, make sure that you resize the image correctly. So in our case, it will be 64 by 64. And then you have to convert it to an array. So if it's your model, I mean, we don't have to resize it at this point, but this is just to ensure we're following what we did earlier. Let's standardize it by making sure the pixels values are here. I need to get used to this new keyboard. And then take in the standardized and reshape it so they also have the same shape, and transpose that. And then plot it. Let's take a look at it now. I did the same typo. There we are. So we have this bird here. This is our image. So let's call this my predicted image equal predict. So go into that dictionary we just created, get me the W value and get me the B value. So this is the same model, and pass in my image. And time for the moment of truth. 1. So that's correct. It is a bird. So it did predict this correctly. That 1 is a bird. So yeah. So this is in our classes. We said 1 is a bird and is here. So thank you all for watching, and I hope you've at least got something out of this, which is basically building a neuron from scratch using logistic regression. What we did is we did data pre-processing. We renamed the files, we resized the images, and then we imported them, creating the labels out of the name. We've showed what the classes are. We have also presented a quick example here. We showed you how to get a general feeling of the data set. We flattened and reshaped it into a column vector for each example. We've standardized the data set. We did a quick walkthrough to the logistic regression. We defined a sigmoid function. We initialized W and B, which are the parameters for logistic regression, with 0. We implemented the forward and backward propagation, including iteration learning rate in a third function, and then we combine all of these under the hat model with the function predict, which shows you if that was predicted correctly or not. We've walked through a learning rate with a certain number of iterations. Then we increase the numbers of iteration with adjusted learning rate with a graph, so you can see the difference, and then you should be able to add your own image and see if your neuron works on new images, or just get a feel of it really. Okay, thank you all.